You're good.
We good? Is it rolling? Oh, good, thank you. Okay, so today we're going to look at functional groups and families of organic compounds. And we might get into some early discussion on organic nomenclature. So if I look at say this compound and this compound and this compound, I find that they have certain things in common. I find that all three of those compounds will dissolve in water. In fact, they're actually miscible in water, which means they dissolve infinitely. And so very, very quickly, if I add table salt or sugar to water, so I add a spoonful to a glass of water, and I stir it and it dissolves, and I know it dissolves because there's no phase separation. Right? I see that all of the solid sugar or salt goes in the solution. There's no residual solid. There's no phase separation. And I can keep adding salt or sugar and stirring it, and it will dissolve. And the point comes when no more will dissolve. And I know that because it's a phase separation. So because it goes in the solution, I say it's soluble. But solubility implies that there is a limit to how much of the solute dissolves at a given temperature. Miscibility means we dissolve, but there is no limit. So for example, I might be able to dissolve 5 spoonfuls of salt in a glass of water, but I can dissolve a cupful of ethanol in water. I can dissolve a barrel full of ethanol in water. I can dissolve an ocean full of ethanol in water. And I will never see a phase separation. So ethanol and methanol, and in fact these 3 alcohols are infinitely soluble in water, so we say they're miscible. So miscibility means infinite solubility. So if I look at these 4 alcohols, I notice that they have certain properties that are alike, and some of those properties are physical, right? So one physical property is that they're miscible in water. Okay. Another physical property is that they have relatively elevated boiling points. So the boiling points are somewhat elevated, and this is true for both their boiling points and their melting points. Okay. So they're miscible in water. They have elevated boiling points and melting points. And those are physical properties. I also find that all of them have certain chemical properties that are similar. For example, they will all react with, say, sodium metal, and they evolve hydrogen gas, and the reaction is actually kind of violent. If I put a piece of sodium, say a pea-sized piece of sodium, in any one of those liquids, the sodium will melt into a silvery ball and dart about the surface very randomly. And in fact, if it gets stuck to the side of the container, it bursts. You see a flame created as the alcohol burns. So it reacts with sodium metal to evolve hydrogen gas. It's pretty to watch. They will react with, for example, acetic acid, right, which is the acid found in vinegar, and they'll create something with a fruity smell. Okay? So they've got certain properties that are similar, and these are both physical properties and chemical properties. So we say that they're physico-chemical properties. We say that they're physico-chemical properties are similar. So I've put some physical properties here, and there's several others. I've put some chemical properties here, and there's several others. So when I look at these four compounds, I have to ask myself, well, what aspect, what feature of the molecules confers upon them similarities in physical and chemical properties? And when I look at them, I can decide, well, look, I'm going to divide this molecule into two parts. I have this part that is common to them all, and therefore it stands to reason that's the part that is the genesis, that is the origin of the similarity in physical and chemical properties. So I'm going to call this unit a functional group. And I can say then that a functional group, and by the way, I have posted for you guys on Blackboard under resources a handout that identifies functional groups and lists them in order of priority, which we'll get to in a second. But it identifies a functional group, and I'm going to read it off here, is a specific collection and arrangement of atoms that dictate the physical-chemical properties of a compound. Okay? So a functional group is a specific collection and arrangement of atoms, and this is important because it has to not just be which atoms, but how they are arranged. Okay, so for example, we've seen this before. I can have a scenario where I have S attached to C attached to N. That's very different from N attached to C. N. That's very different from C attached to S attached to N. Right? It's a very different scenario. So I can draw this in a couple of ways. I can do that. So let's see. So 1, 2, 2, so 2, 4, 6, 8. Minus. So 2, 4, 6, 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. So 1, 2, 3, 4, 5. This must be 1 here too. So 2, 4, 6, 8, 10, 12, 14, 16. So I have 0, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 4, 5. Yeah. No, that's not quite right. So I have, so 2, 4, 6, and 1 is 7. And then I have, you know what, we'll pick a different example. So I can have O, N, double bond, O. Or I can have N, double bond, O, O minus. That might just be easy. So these both have NO2s. There's one N and two O's, but the arrangements are different, right? So in other words, I have a carbon in this case that's directly attached to the O, and then that's attached to N double bond O. Or I can have the carbon attached to the N, which then has O and O on it. So although they have the same collection of atoms, the arrangements are different. Okay, let's just do that. So a functional group is a specific collection and arrangement of atoms that dictate both the physical and chemical properties of a species. So everything having an OH group is going to tend to be miscible, if not soluble in water. And there are rules we talk about in a little bit as to how many carbons one OH can pull into solution. They would tend to have elevated melting points and boiling points. They would all react with sodium to form hydrogen gas, and they would all react with what we call carboxylic acids. Acetic acid is one, to give compounds called esters. And all esters have fruity smells. Well, if that's true, then I can divide organic molecules by and large into two parts. There is the functional group part, which dictate the physical and chemical properties. And then there's the, what you might call the organic part, the carbon-containing part, which is the rest of this. So I can really then say that all of these compounds belong to a family that I can describe as ROH. So OH is the functional group, right? It's the functional group which dictates the physical and chemical properties. But the R is the organic variable. So in math, our variables are, A, B, X, Y, and so on. In organic chemistry, the variable is uppercase R. And R represents what we call the alkyl group. So while the functional group dictates the physical and chemical properties, the alkyl group sort of fine-tunes it. So what you find is that the R group, as it gets bigger, the compound tends to get less and less water soluble, right? So the alkyl group kind of fine-tunes or attenuates, but the functional group is essentially what drives the physical chemical properties. So it stands to reason then that it's important for us as organic chemists to have a handle on what are the common functional groups, and to understand their chemistry, both the physical properties and the chemistry, but also to have a handle on the common alkyl groups. Because the combination, the marriage of the alkyl group and the functional group, that combination tends to, for an organic chemist, as you glance at the structure of the molecule, you're looking at the alkyl and the functional group, and you can, pretty much determine what you expect this compound to do. You can determine its behavior, right? What is it likely to do? Because those are dictated primarily by the functional group, and they are mediated by the alkyl group. So what we're going to do is to look at the common functional groups and to look at the common alkyl groups. So at this point, I'm going to expect you to download this document, which is on Blackboard, and we walk through the various functional groups. And the functional groups lead to what we call families. They lead to what we call families of organic compounds, or classes, right, of organic compounds. In the bad old days, these were called homologous series. So alcohols, these compounds of the general formula ROH, are called alcohols. So alcohols represent a family of compounds, or it's a class of organic compounds, or it is a homologous series of organic compounds. All right, so let's walk through the functional groups, and we'll build our way up from the bottom. And I won't, since they're on the sheet, I will not spend a massive amount of time developing them. I will point out that there are a couple that we will not meet a great deal in this class. So we will meet the one at the very top, the cations, the ammonium ions. But we'll not spend a lot of time on them. And then lower down in the list, about maybe about 2/3 of the way down, there are thiols, or what are also called mercaptans. We're not going to spend a massive amount of time on those either. But all the others are going to be, same with the sulfides, which are 3 entries below those. The others we will see a fair amount of. Okay, so alkanes, the simplest class of organic compounds are alkanes and alkanes. Alright, so let's talk about alkanes. And alkanes have the general formula CnH2n plus 2. These are for acyclic alkanes. We'll get that in a second. So, for example, I can have, well, in fact, so I can have, right, my value of n, so n can be 1, let's say 2, 3, 4. And my formula will be, so let's say formula, and then I'm going to put structures. So when n is 1, I have CH4, and that's going to be simply C with 4 H's on it. When n is 2, I have C2H6, and that's going to be C 2H6. When n is 3, I have C3H8, and that's going to be C3H8. When you get to n is equal to 4, then you get to isomers. So this is C4H10, and there are a couple of versions of C4H10. Either I can have them all in an unbranched arrangement, what we often call straight chain. Okay? So I can have all 4 carbons together in an unbranched or straight chain. Or I could have 3 of them and then have the 4th carbon on the middle carbon. Now, if I put the 4th carbon here, that is the same as doing this. Because what you want to mentally do is kind of walk your finger along from one end to the other. Right? So in this case, I have all 4 carbons in a line, and I don't have to back up to include another carbon. But here, if I went this way, I'll have to back up to include that carbon. If I go this way, right, like this, I'll have to back up to include that carbon. So these are 2 different skeletons completely. Right? But these are both C4H10. Okay? These are both C4H10. And as you have more and more carbons, you have more and more isomers that become that form. So these are alkanes. So alkanes only have, with the exception of methane, only have carbon-carbon single bonds, and of course they have carbon-hydrogen bonds. And those are going to be single bonds. It turns out there is another class called cycloalkanes, which have the formula CnH2n. Because if they are monocyclic, right, this is for monocyclics, if they are monocyclics, then they will have one HDI, and therefore you will be missing 2 hydrogens. If they were bicyclic, it would be CnH2n minus 2, and so on and so on. And you can start to get rings at 3 carbons. So I could have this. I have this one. Right? So this is called cyclopropane. Oh, I didn't put the names here. Well. Yeah, okay. Might as well. This is called cyclopropane. And this one, I'll just write like this, which is 4 carbons. That's called cyclobutane. So let me just, while I'm on this, so the name, out of giving this one, the name, this would be methane, which is marsh damp or natural gas. So the gas that goes into your homes that you cook on is methane. This is ethane. This one is called propane. Propane is the gas that is found in, when you go to barbecue and you have a gas barbecue, the gas that's in those tanks is propane. So it's liquid propane gas, LPG. This one is called butane, and for the moment I'll take this one off. This is called butane, And for those of you who smoke, which I'm hoping none of you do, but the gas that's in, the liquid that's in the cigarette lighter is butane. Okay? I want you to notice that in all of these compounds, there is a suffix of ane. And the suffix ane is because we're dealing with alkanes. So all of these compounds are alkanes, which I recognize, not just from the molecular formulas, right? But from the suffix being ane. And what we do when we talk about this when we get to nomenclature is the prefix tells you which alkane. So meth implies a 1-carbon alkane. F implies a 2-carbon alkane. Prop implies a 3-carbon. And but implies 4 carbons. So it turns out that the prefixes, the prefaces, give you information as to how many carbons are in the unit, right? Simply. And then the suffix tells you what is your class of compound. Now, if I have a 3-carbon species that is cyclic, well, it's an alkane in the sense that it only has carbon-carbon single bonds and carbon-hydrogen single bonds. That's alkane. It's got 3 carbons, so it's propane, but it's a ring, so it's cyclopropane. This one only has carbon-carbon single bonds and by extension and also carbon-hydrogen single bonds, so it's an ane. It's got 4 carbons, so it's a butane. And it's a ring, so it's a cyclobutane. Okay? So we've jumped ahead a little bit in that we're talking about a systematic way of naming organic compounds, which is your naming scheme or your nomenclature, which we get to in a little bit. Okay, so I want to talk a little bit about some substructures in alkanes. So I can draw any number of alkanes on the board. So let's draw that one, let's draw this one, and this one. So we are going to subclassify the carbons of an alkane based upon the number of carbons it is bound to. We're going to subclassify individual carbons in an alkane based upon the number of other carbons that it's bound to. For example, this carbon is bound to 1 carbon directly. So yes, there are a bunch of carbons in a molecule. I'm not interested in all of them. I'm only interested in how many carbons is this carbon directly bound to. So this carbon is bound to 1 carbon. So I will call this carbon a primary carbon, and I'll represent it as 1, it looks like 1 degree, but it's called primary. This carbon is attached to 2 carbons. So I'm going to call this a secondary carbon. Right? By that token, this carbon, which is also bound to 1, 2 carbons, this is also a secondary carbon. And this carbon would be a primary carbon. It's bound to 1 other carbon. If I look at this structure, how would I classify those carbons? Well, this one is primary because it's bound, here's my carbon, it's bound to 1 carbon. Are there other primary carbons in the molecule? Absolutely. This one is primary. This one is primary. Right? This one is primary. This one is primary. All of those are primary carbons. They're all bound to 1 other carbon. Are there any secondary carbons? Well, let's see. This carbon is bound to 1, 2 carbons. So this is a secondary carbon. Are there any others? Well, this one is bound to 1, 2, 3. So this is a tertiary carbon. That's spelled tertiary. That's a tertiary carbon. This carbon carbon is bound to 4 other carbons. 1, 2, 3, 4. So this one is a quaternary carbon. It's a quaternary carbon. So carbons then will fall into, as I've drawn them, into 4 classes. There will be primary carbons, secondary carbons, tertiary carbons, quaternary carbons. Now, carbons like those of methanol, are in a class by themselves because they're not bound to any other carbon. Okay? So that we don't have a specific name for those. Just consider these to be in a class by themselves. It does also mean that there are no such things as, you can't have a carbon of that type because the limit to the valence of carbon is 4. So the most carbons we can be bound to, so you can't have pentanary carbons, the most carbons you can be bound to is 4 because the valence is 4. So either you're bound to none, as a methanol, a subclass by itself, or you're bound to 1 primary, 2 secondary, 3 tertiary, 4 quaternary. That's it. So we can subclassify carbons in alkanes, and for that matter, in organic compounds. So beyond alkanes, and by the way, this would be true whether we're dealing with alkanes or cycloalkanes. So let's look at a cycloalkane and classify those carbons as well. So if I have a cycloalkane, so this would be a cyclopentane, right? Cyclo, 1, 2, 3, 4, 5 carbons, only carbon-carbon single bonds, so a cyclopentane. If I were to draw something like this, right? Then I have these would be primary. These would also be primary, right? Because each of these attached to 1 carbon. I'll have a bunch of secondaries. That's secondary. This is secondary. This is also secondary. This carbon is attached to 1, 2, 3 carbons. This is tertiary. This carbon is attached to 1, 2, 3 carbons. That's also tertiary. And then this carbon finally is a quaternary carbon. So we can classify all the carbons in the molecule as primary, secondary, tertiary, or quaternary. There are also alkenes. And alkenes are compounds that have carbon-carbon double bonds. So alkenes could have, so the simplest would be this compound. And then I can have that one, and I can have any number of others. So there's a way to subclassify alkenes. So all of these are alkenes; they're a class of compounds. But I can subclassify the alkenes in different ways. This alkene has no alkyl groups on it, right? In other words, this essentially will have H's. So I'd say this is an unsubstituted alkene. This will be mono-substituted. It's got 1 alkyl group, so it's mono-substituted. And these 3 are di-substituted. Right? These 3 are di-substituted. Okay? Now, within these, both of these alkyl groups are on the same carbon, carbon 1. So I'll say this is a 1,1 disubstituted. Whereas the ones at the bottom are 1,2. In other words, I've got alkyl groups on carbon 1 and carbon 2. Carbon 1 and carbon 2. I've got a methyl group on both of those carbons. Remember, this is CH3 or methyl. So both of these would be called 1,2 disubstituted alkenes. And if you remember the previous lecture, this one is trans because the groups are on opposite sides of the double bond. If I take my double bond as a frame of reference, here my alkyl groups are on opposite sides, or if you want, the H's, which are understood, are on opposite sides. This is the trans one, whereas this is cis. Here the alkyl groups are on the same side, or if you want, the H's, which we don't normally draw, are on the same side. It doesn't stop here, because I can have alkenes that are tri and tetra substituted. So this would be an example of a tri-substituted alkene. So tri-substituted. And this would be an example of a tetra-substituted alkene. Right? This is tetra-substituted. So I can subclassify alkenes into whether or not they are unsubstituted, mono, di, and di comes in several flavors. There is the 1,1 di, where the two alkyl groups are on the same carbon, and then there's a 1,2 di, where they're on adjacent carbons. And they can be subclassified as either trans or cis. We talk about this some more. They can be tri-substituted, or they can be tetra-substituted. One last point. When the double bond appears at the end of a chain, it is said to be a terminal alkene. So these two can also be considered terminal alkenes. Right? Because they end the chain. There are no more carbons beyond this one. I would call these internal alkenes because the double bond is inside the molecule. It doesn't have to be exactly in the middle, right? But it means that the double bonds, the vinylic carbons, the carbons that make up the double bond are flanked by other carbons. So these are what we might call internal. So these are internal double bonds, or the internal alkenes. So alkenes are another class of organic compounds. They contain the carbon-carbon double bond unit, which is called the vinyl group. So the vinyl group, which is a functional group of alkenes, is C double bond C. The carbons in the vinyl group are called vinyl carbons. Some people call them vinylic carbons. So these are vinylic carbons, okay? And there are ways in which we can subcategorize and subcategorize alkenes. They can be terminal or internal. They can be unsubstituted, monosubstituted, di, tri, tetra. And the dies can be either 1,1, 1,2, and the 1,2 cis or trans. There are alkynes, which is another class of organic compounds. And alkynes have the carbon-carbon triple bond. Oh, I don't think I wrote this. So these carbons are called vinylic. These carbons, the carbons in a double bond, are called vinyl or vinylic carbons. The other class of hydrocarbons would be alkynes. And alkynes, which, and we have met this in one of the previous lectures, they have the carbon-carbon triple bond unit, which is often called the acetylene, or the acetylenic group. And so alkynes fall into two categories. They can either be internal, where I can have either the same R groups or different ones, or they can be terminal. Right, so this is a terminal alkyne. Where the triple bond ends the chain or begins it, right? In our perspective. This is an internal alkyne. And so examples would be, this is an internal alkyne. This would be a terminal alkyne. Okay? Going up the list, we mentioned nitro groups in the example that we gave earlier. So if I have nitro compounds, so I have a species called nitroalkanes, which basically are R and double bond O minus plus. Those are examples of nitroalkanes. There are also, we won't see this a lot in this class. We'll see a bit more in organic too, but even then there's a limit to how much of the chemistry of this we actually study. And while we're on it, we'll distinguish these from what are called alkyl nitrites, since I brought it up earlier, which are isomers of these, but have a different connectivity. So they're connected that way. And the chemistry of alkyl nitrites and nitro compounds are very different. In fact, a lot of the compounds that we take to increase blood flow are alkyl nitrites, because when you ingest them, this bond cleaves and you generate NO. And NO is a vasodilator. And so people who are having a heart attack, one of the things they do is they ingest compounds that are alkyl nitrites, and the NO group is released and it dilates blood vessels. Nitro compounds don't do that. Okay, so the chemistries are different. Even though it's the same N, even though it's an N and two O's, so it's the same collection of atoms, it's not the same arrangement. And in chemistry, structure and function, structure and behavior are intimately related. Okay? So alkenes, alkynes, alkanes, nitroalkanes, and alkyl nitrites. There are also haloalkanes. Halo is from halogen, or halogen. These are the group 7 elements, the fluorine, chlorine, bromine, iodine. We work about astatine in organic chemistry. So fluorine, chlorine, bromine, and iodine. The haloalkanes can be subcategorized. And they are subcategorized based upon the character of what we call the alpha carbon. So let's say I have that compound, that compound. So this is a fluoroalkane, a chloroalkane, a bromoalkane, and of course I can have iodoalkanes. So fluoroalkane, chloroalkane, bromoalkane, iodoalkane. So I can categorize them based upon the identity of the halogen, and that's relatively trivial. The carbon attached to the halogen is referred to as the alpha carbon. call this the alpha carbon. Carbons attached to the alpha carbon would be the beta carbon. This would be the gamma carbon. This carbon is alpha, this is beta, this is gamma. I'll call this one beta prime. Okay? This is alpha, beta, gamma. I can call this beta prime, beta double prime. But it turns out these are actually equivalent, so I'm just going to call these the beta prime carbons, right? So I have the carbon attached to the heteroatom. When it's singly bonded, talk about it in some more detail, it's called the alpha carbon. And then you go alpha, beta, gamma, delta, epsilon, and so on. And for organic, you know, you really want the sequence, you know, alpha, beta, gamma, delta, epsilon. That's about as far as you will tend to go. If the alpha carbon is primary, this is called a primary haloalkane, or more specifically, a primary fluoroalkane. So here's my alpha carbon. It is bound to one other carbon. So I'm going to classify this as a primary fluoroalkane. How do I classify that? Well, it's a chloroalkane. The alpha carbon is bound to two carbons. So that's a secondary chloroalkane. So this is a secondary chloroalkane. That's a bromoalkane, where the alpha carbon is tertiary. The alpha carbon is bound to three alkyl groups, so or three carbons. This is a tertiary bromoalkane. And not surprisingly, this one would be a secondary iodoalkane. Secondary iodocycloalkane. Okay? So if I were to classify those as tightly as I could, that would be a secondary iodocycloalkane. We can also classify there are other classes of organic compounds. Thiols. Well, we can have, let's do alcohols. So there are alcohols. Oh, well, one thing. Haloalkanes are often written as Rx, where X represents the halogen. Right? So R is your variable, right? Your methyl, ethyl, propyl, and so on. And then X would be the halogen, which is also a variable, because it would be fluorine, chlorine, bromine, or iodine. So we typically write them as Rx. Alcohols we saw earlier are ROH. And we can classify alcohols in lots of ways. Now, we will do some of it now. There are other ways of classifying which are really meant for second organic, so we won't get into those. But we can classify alcohols in the same way that we classify haloalkanes. So I can have, let's do it this way. So my alcohols fall into four classes. And I could have done the same thing with those. So I have methanol, which is a one-member class. Right? So let's just call this methanol. Then I have alcohols where the alpha carbon, one bound by a single bond to the heteroatom, the alpha carbon is bound to one R group. So this is a primary alcohol. Here the alpha carbon is bound to two R groups. That is a secondary alcohol. Here, the alpha carbon is bound to 3 R groups. This is a tertiary alcohol. And by the way, there can be nothing like a quaternary alcohol or a quaternary haloalkane. Because from the time I say it's an alcohol, it means I've used up 1 valence of the carbon to bond to the OH. I'm only allowed 3 other valences. So the most I can have is 3 R groups. So the highest level, if you will, of the alcohols is tertiary. Same with the haloalkanes. Once I say my haloalkane, I've used the valence of the carbon to bond to the heteroatom. I'm only allowed 3 more. So either I'm bound to 1 R group, well, I'm bound to no R group, so I'm methyl chloride or chloromethane or whatever. I'm bound to 1 R group, so I'm primary haloalkane. 2 R groups, I'm a secondary haloalkane. 3 R groups, I'm a tertiary haloalkane, a kind of a quaternary one. So I can subclassify alcohols based upon the identity or the character of the alpha carbon. There are also, beyond haloalkane, beyond alcohols, I have thiols, and thiols are basically relatives of alcohols where we replace the O by a sulfur. So instead of an alcohol, right, we're going to have a thiol. That's simply RSH. And so I'm going to replace all the O's by sulfurs, and everything I said about them will remain the same. So that's the methane thiol, right? That's called methane thiol, which is a 1-member class, and then that's a primary thiol. This is a secondary thiol and tertiary thiol. Okay? Right, so one R group on the alpha carbon, 2 R groups on the alpha carbon, 3 R groups on the alpha carbon. Thiols are very interesting compounds for any number of reasons. The most trivial, I guess, is that they all stink. You guys may remember from high school or even Gen Chem, it was kind of a kick to make H2S, hydrogen sulfide, which smells like rotten eggs. Anything with that SH unit stinks. So if you think anything you can think of that has a, well, that's not true. Many things that you can think of that are foul smelling are thiols. They smell badly because they contain some amount of thiols. So skunk perfume is jam-packed with thiols. Onions, garlic, jam-packed with thiols. If you eat lots of beans or meat, and then an hour later you start to lose friends because of gaseous exhaust, a lot of those fumes are thiols. Okay? Okay, so those are thiols. Both alcohols and thiols form derivatives. So instead of having ROH, like in an alcohol, or RSH, as in a thiol, they can actually give you species that are ROR prime, RSR prime. These are called ethers. These are called sulfides. By the way, another word for thiol is mercaptan. Okay, so the terms thiol and mercaptan are interchangeable. Okay, so we won't study thiols and sulfides to any great degree, just to mention them. Although there's a wealth of chemistry with particularly thiols. We will study ethers in detail in organic 2, not so much in organic 1. Amines are very interesting. So amines are compounds that have an have R attached to N. So if I have RNH2, these are called primary amines. And I'll make the point in more detail in a second. These are called secondary amines, and these are called tertiary amines. Now, this is very different. From how we classified alcohols, haloalkanes, and thiols. Because if you recall, we classified those based upon the character of the alpha carbon. Okay? So this was a primary alcohol. This was a secondary alcohol. This was a tertiary alcohol. With amines, we don't worry with the character of the alpha carbon. We classify the amine based upon the number of alkyl groups attached to the nitrogen. Okay? So the nitrogen has one R group, regardless of its character of the alpha carbon. If it has one R group, it's primary. 2 R groups, it's secondary. 3 R groups, it's tertiary. Now, this is important. So let's look at, let's do a comparison. So I just drew a primary, secondary, and tertiary alcohol on the board. If I had this, that's a primary haloalkane. This is a secondary haloalkane. This is a tertiary haloalkane. However, this, and this, these are all primary amines. Right? We don't care that the alpha carbon is primary, or secondary, or tertiary. That is all that is needed to classify alcohols and haloalkanes. But to classify amines, we don't look at the character of the alpha carbon. We look at how many carbons are attached to the nitrogen. So all of these are RNH2. Whether the carbon that's attached to the N is primary, secondary, or tertiary, it doesn't matter. If I have RNH2, those are all primary amines. So the way we classify amines is very different from the way we classify alcohols, thiols, and haloalkanes. And that's very important to remember. So I could, if I were to draw something like this and ask you to classify the amines in this compound, right? If I was to classify the amines in this compound, okay. Well, this is primary, right? This one is primary. This one is secondary, right? Attached to 2 R groups, that's secondary. And this one is tertiary, where the N is attached to 3 carbons. So primary, secondary, 2 carbons, tertiary, attached to 3 carbons. Okay? We're nearing the end of our functional groups. And we could look at compounds that have, these are carbonyl compounds. These are compounds having C double bond O. So carbonyl compounds have a C double bond O group. This is called the carbonyl group. The carbonyl group has a carbonyl carbon and a carbonyl O. So this is the carbonyl carbon, this is the carbonyl oxygen. Okay? So the compounds that contain carbonyl groups fall into several categories. And the one category is an aldehyde. These are called aldehydes. In an aldehyde, I must have C double bond O attached to H. It's also written as RCHO. So I must have the carbonyl carbon attached to at least one H. What's interesting is that this R can either be an alkyl group or it can be an H. So it can be an R or an H. So the simplest aldehyde is this one. Right? This is referred to as methanal. Okay? See, meth implies one carbon. Al implies it's an aldehyde. Aldehyde. So examples of aldehydes might be this. That's an aldehyde. Right? That's an aldehyde. This is an aldehyde. So all of those are examples of aldehydes. Related to aldehydes are compounds called ketones. Ketone, the word ketone, does not have a Y in it. I'm going to say it again. Ketone does not have a Y. It is Ketone. Ketones, these groups that flank the carbonyl carbon, must be carbons. Right? So, what it means then is the simplest ketone must have 3 carbons. The carbonyl group, which is understood for a ketone, and since the carbonyl group must be flanked by carbons, there must be at least 1 carbonyl and 1 carbonyl. So the simplest ketone has 3 carbons, which is interesting because the simplest aldehyde can only have 1, can have only 1. So the simplest ketone is this compound, right? This is called propanone. It's called propanone. It's also called acetone, which is the common name for it, right? Which you use as a wash solvent in the organic lab. So examples of ketones would be something like this. That's a ketone, or this is a ketone, or this is a ketone. Right? So all of those are ketones. Now there's something interesting about the way we label. Remember a second ago we talked about alpha, beta, gamma, and delta carbons? With carbonyl compounds, whether they are aldehydes or ketones, whereas in alcohols, amines, haloalkanes, and so on, where if we had the alpha carbon singly bound to X, where X could be OH, Cl, NH2, SH, and so on. This was alpha, beta, gamma, delta. So when the alpha carbon, so when the